So let us get into the business of today's class. We'll be dealing with IUPAC nomenclature. We'll be dealing with what? IUPAC nomenclature. Thank you for reminding me that. I say I really didn't want to do this today. So the very first structure that we have, we're going to look at here is JAM 1979. It's a JAM question, and we have this IUPAC nomenclature. Yeah. So we are asked the IUPAC name for this compound. And what was given to us is CH3, C, CH3, then H, CH, double bond, CH2. The IUPAC name for this structure is what? We have the options provided here, 2-methyl-but-3-ene, option A. Option B is 2-methyl-but-4-ene. Option C is 3-methyl-but-2-ene. Option D is 3-methyl-but-1-ene. So we're going to find out what the correct answer is. Like I had stated, the first thing you deal with, whenever you want to give the IUPAC name of a compound, is identifying the functional group that you have there. Why determining the longest chain? Are you getting me right? These two things have to be considered at the same time. Yes. Unlike alkanes, where straight ahead you go to finding the longest chain. Are you getting me? By the time you start dealing with other functional groups, you try to determine the longest chain while respecting the active functional groups. Are you getting me right? Because the rule is that you must count in all the direction that contains all reactive functional groups. Are we together? So, but structures you meet in your exams, JAMB and WAEC, they are very simple. Just have that in mind. Yeah, have that in mind. If I ask you, what's the longest chain here, what will be your answer? 4, is that not so? Most of us, if not all, are aware of that. 4 is the longest, which could go 1, 2, 3, 4, is that not so? And remember, I've counted from left to right. I could have counted from what? Right to left. We learned from our previous class that you must determine where you start your counting from. Are you following, right? We know that the longest is 4. We could have also gone this way and get the same 4. Is that not so? But there's something I told you from our previous class. The direction you take, if the longest chain has the same number as the what? Branch. For me, so that I don't stress myself, I usually take the straight chain as the longest. So the other guy will consider it as what? A substituent. So we have known that the longest chain is 4. And because it is 4, the parent name will end with what? But. The question now is but what? Is it but-in, but-in, but-ein, but-anol, but-anal, but-anon? Depending on the functional groups we've learned so far. Are you getting me right? Or is it but-anoic, acid, whatever you want to call them? So this will now help us to, this will take us to now look at the active functional group here. Are you following, right? What is the active functional group you're seeing here? Alkene functional group, which is this what? Double bond. So it's going to be but-in. But-in is an alkene group. But then here comes the question, which carbon atom has the what? In, the double bond. Are you following, right? You have to determine the carbon atom. So it will become but a number E. Are you following, right? For us to know the carbon atom that has this double bond, we need to know where counting should start. In this structure, where we counting start from. Remember, unlike alkanes, for alkanes, you use the attachment, the substituent, to determine where counting will come from most generally. Are you getting me right? Although our questions say we are picking them randomly, like I said. This is an alkane, by the way. Apart from alkane, the other homologs, where you start your counting from, is the side that is closest to the functional group. But like I said, there's another rule. You count from the direction that gives the lowest sum. Are you following, right? To either the attachment or the functional what? Group. But please have this in mind. The first rule you consider for any other homolog apart from alkane to determine where you start your counting from, the first thing you must consider is the side closest to the what? Functional group. So what do you say based on that? Where will you start your counting from here? You are very correct from the right hand side. So without wasting time, let's go. Now you notice that there is a carbon atom we did not count among the parents. Is that not so? Which carbon atom here? This CH3. As a substituent, the name of this attachment, this substituent is what? Methyl. You are very correct. Is there any other substituent here? No. So we are now ready to give the IUPAC name of this structure. Are you getting me right? Are you ready? Are you ready? In giving the name, you mention the substituent first, the attachment. Is that not so? Indicating the parent carbon bearing the attachment. True or false? So the attachment here is what you said, methyl. On which parent carbon atom position are you saying it? 3. So it's going to be what? 3-methyl. Any other substituent? No. So the parent name comes in. Is that not so? The parent name here is what we said, the prefix first. Good. Now, we started counting from here. After this first carbon atom, you see the functional group. I told you that carbon atom you will count before you see the functional group. For alkene and for alkyne, are you getting me right? That carbon atom is assigned the double bond. Am I communicating? So after carbon number 1, you see the what? Double bond. So this is going to be but what? 1. But 1 and what? In. Very interesting, simple, is that not so? And sweet, just like Precious is enjoying right now. Okay, let's go. So the name of this guy is simply 3 what? Methyl, but 1 in. That is it. Oh. If you go to the options provided, you locate which one has this. And from what I'm saying here, option D, 3-methyl but 1 in. But first, let's move on to our second question. No time. I have set the foundation already, so you're following up. And even before we started organic chemistry, I dropped a video lesson link. Is that not so? That covers everything about organic chemistry for you. So this is much like a revision, so to say. The next question I have here, which is our second question for our class today. Oh no, I was thinking this. That has to be silenced. I don't know. Okay. I was worried already. Mrs. Ifezwe, welcome to join the class. I was going to make reference as to whether you've connected, actually. I'm glad to see you there. So we are looking at the second structure. You check if the thing is showing. All right. The second structure, please, let's move. JAM 1980. JAM 1980. The year doesn't matter with respect to the structures given. Take notes. We are required to give the IUPAC name. We are required to give the IUPAC name of CH3, CH2, C, CH3, double bond C, CH3, then CH3. IUPAC name of this guy. Are you following? Without wasting time, let's analyze. I don't believe all of us know what the longest chain is going to be. 1, 2, 3, 4, 5. 1, 2, 3, 4. I think 5 is the longest. Is that not so? Counting will start from where? Without being told, counting will start from the what? Right. Because the double bond is closest. Are you following right? You have 1, 2. After the second carbon atom, you see the double bond. If you are counting from the left, 1, 2, and 3. After the third carbon atom, that's where you're seeing the double bond. So which direction gives the lowest sum? From the right. Are you following right? Good. So we have 1, 2, 3, and what? 4, 5. Is that not so? Now you notice that this guy was not counted, so it becomes a substituent. This one also is what? A substituent. True or false? On which carbon atom do you have this attachment? 2. Is that not so? Yes. On which carbon atom do you have this attachment? Good. What is the name of this substituent? What about this? Are they different or the same? When they are the same, what do? identify the position together. Is that not so? Use comma to separate the numbers. Okay, yeah? So let us do that. The IUPAC name would be, on the second carbon atom, you have a methyl attachment, comma. On the third carbon atom, you still have a methyl attachment. Since it is the same group, are you following, right? You bring out the position of the carbon atom bearing there. 2, 3. How many of these methyls do we have? 2. You use the Latin number for 2. And the Latin number for 2 is what? So dimethyl. You are telling us there are 2 methyls there. Dimethyl. Now the longest carbon chain is what you said. Give me the prefix. Pent. Which parent carbon atom will be assigned the double bond here? 2. Because after the second carbon atom you say the double bond. So it's going to be pent what? Very simple, is that not so? Or very difficult? Organic chemistry is very simple. I keep saying this. When you come to the concept of IUPAC nomenclature, these things are 1 plus 1. They are. It's just for you to get a good coach that explains this for you, break them down. And of course, you see that any IUPAC nomenclature question given to you in your exam, WAEC and NECO, and or JAM, will just be a bonus question for you. Are you getting me right? It's a bonus. Now we have given the name of this structure. There's something I want us to do before we move on to another structure. But by the way, let me read out the options. Option A is 2, 3 dimethyl pent 2, 3 in. Is that the answer? Option B, 2, 3 dimethyl pent 2 in. Is that the answer? No need of reading the other options. Now this is what I want us to do. I want us to write the molecular structure of these guys. Because what we have been dealing with is structural what? Formula. These things where these guys have been exposed, we call them their structural formula. Are you following, right? We can write these structures in condensed form. In what I said? Whereby you pick the parent chains, you write them out, and any attachments you have will be enclosed in brackets. It's possible you've seen a structure like that before, where the structure has not been expanded. Are you following, right? Let me teach you that quickly, because an examiner can give you something like that and ask you to give the IUPAC nomenclature. As a matter of fact, this evening I'm going to answer one question like that via our channel. I'll drop that. See, if you come here, you have CH3, is that not so? I want to condense it for the first structure. CH3. Here, still part of the parent chain, is that not so? C. What is attached to it? Hydrogen. You know, hydrogen is not an attachment anyway. It's not considered a substituent. So it's going to be this parent carbon chain, this parent carbon atom is bearing hydrogen. Are you following, right? Is there a substituent on it? Yes. Is there a substituent on it? Yes. Because there's a substituent on it, you open a bracket. You open what? Then write that substituent in bracket there. Assuming there are 2 substituents on this same carbon atom. Last class, there is one structure we saw something like that. Is that not so? Where the attachment, the substituent was repeated on the particular carbon atom. Let me assume this hydrogen happened to be CH3 as well. It means that this parent carbon is bearing how many substituents on it? 2 the same guys. Are you following, right? It means that if you write this CH3 in bracket, you step down 2 atoms. That is atomicity of the CH3. There are how many of them? 2. Are you following, right? Good. Then you proceed. You come to this guy. You have, that is parent carbon. Is that not so? So you have your C and then have your H. After that, what do you see? Double bond. Because you need to indicate that this is a doubly bonded compound, an alkene. And then finally, what do you see there? CH2 as part of the parent carbon. So instead of someone expressing the formula like this, which is the structural formula, are you getting me right? This could have been used. Molecular structure. Are you following, right? Molecular what? Structure. We can go ahead to condense sometimes too if the structure really requires condensation. Yeah, although it all depends on the type of structure given to you. I will show you something when I condense this. Are you following, right? When I bring out the molecular structure of this guy, I'll show you something. I'll show you something. But before we move on to that, please, what I brought out here, do you understand it? Do you understand it? If you are given this and you are required to give the IUPAC name, it follows the same principle. Are you following, right? Determine where counting will start from and the longest chain. Do you get that right? Any group that is written in brackets is considered a substituent. It's considered what? But when that guy is written in parentheses, all this bracket is saying, it usually happens if the substituent is an alkyl group. If the substituent is what? An alkyl group. That's why CH something. Are you following, right? They put it in bracket. If it is any of that substituent that I told you, you may also be exposed to. You can have the halogens as a substituent. Chloro, bromo, iodo. Is that not so? If those are the substituents you have, no need of putting it in bracket. You may not see it in bracket. Are you following, right? For example, let me assume that this thing is bromine that is attached. You could see it as CH3, CH, and what? Br, like this. Then CH, double bond, CH2. Do you understand that, right? The reason why we put these guys in parentheses is because they contain carbon as well, too. Are you following, right? And we want to differentiate between the carbon substituent and the carbon parent. Is that clear? That is why if you have an alkyl substituent, you enclose it in what? Bracket, in parentheses. Do you understand that, right? So if you give me this in exam hall, and much more if this is given to you in exam hall, quickly look at if there's any place you have any CH something in parentheses. That guy is a substituent. That guy is what? Good. Determine the longest chain and where you start counting from. First, if we talk about where to start counting from, it's from the right because the double bond is closest there. Is that not so? So you now have 1, you have 2. Will you count this carbon? No, because it's a substituent. So you come to this 3 and what? 4. Telling you this is put something in. Are you following, right? After carbon number 1, you see your double bond. Therefore, it is put what? 1 in. Is that not so? And then on which carbon atom do you have this substituent? Pay attention. Anytime a substituent is given to you, the substituent is attached to the carbon atom it is in front of. Are you getting me? Counting, moving from the left to the what? Right. That one has nothing to do with where you start your counting from. Are you getting me right? I give you a structure like this. How would you know the carbon atom bearing the substituent? It is that carbon atom that the attachment, the substituent, appears just in front of. Are you following, right? And you judge that going from the left to the what? Right. Looking at what I counted here. This is carbon number what? 3. This CH3 is in front of it. Is that not so? Telling you that it is this third carbon atom that has this what? Substituent. With this analysis, the name will still give you 3 what? Methyl, but 1 what? A. Is that clear? Let's condense this one quickly. Let's bring out the molecular formula. Once again, you start. This is what? CH3. After that, CH2. After that, C. And what did you notice? A substituent. What do we do to the substituent? Put it in parentheses, in brackets, yeah, because that guy is an alkyl attachment. Are you following, right? Then after that, what do you see? Your double bond, you have to indicate it to show that it's an alkane. Are you following, right? If it is alkane, hey, what's the functional group of alkane? What is the functional group of alkane? Single bond. Don't tell me one guinea. Single bond. Are you following, right? For that, you may not need to show it. Are you getting me right? But if it is double or triple, you must show that guy. Now, after that double bond, what do you see next? And then there is a substituent there. So you have your CH what? 3. And finally, what do you have? CH3. Now, you see this structure. We can still compress it more. We can. This molecular structure can still condense it more. How? Watch. Come over to this. You notice that there is no attachment here. No substituent on any of these 2 carbons. Are you following, right? So you can compress them directly by counting how many carbons you have there. 2 carbons. So it becomes what? And how many hydrogens? How many hydrogens? 5 hydrogens. So C2H guinea, H5. C2H5. From here to getting me right? And after that, you have this. Does that make sense? So that is C. Then in parentheses, CH3, double bond C, in parentheses, CH what? 3. And then CH guinea 3 like this. Whenever condense that particular carbon, are you getting me right? So you don't touch this part. You can't write this one. Look at this. You can't write this part like the way I condensed this. Are you following? Imagine somebody thinking of writing this as C2, then in brackets, CH3, then 2 outside. Come on, it makes no sense. Are you getting? Because number one, you would have hidden the double bond. Somebody will not know that double bond is there. Are you following, right? And then number two, writing CH3 and then 2 outside on C2 like this, there is no justification to show us really that this thing is on each of them separately. Are you getting me, right? So most times, examiner doesn't bother you there. All right, I just want to open your eyes to something like this in case we meet any. Are you following, right? In case we do what? Meet any. And something is telling me that I should go and look for any, so that we can meet any. Yes, question. Somebody has a question to ask, but before the question, let me see if we can meet what? Any. So that we can answer any. But it seems like I'm not seeing any. But I must see what? Any. Because even if I don't see any, you know, you are dealing with GMAETS41. I must create any. I must. Because I know very well that examiners test you on that, where they will give you the molecular structure. Are you getting me, right? All right, let me take your question quickly before we move on. You can come forward if you want to show. If you have C2H4, C2H5, which one? This. If I have something like C2H5 on the terminal carbon, and perhaps it's in brackets, the question now is, should a good examiner do that? But if it does happen, it's not taken as a substituent. I have said this thing before. When you have a straight chain, you have your terminal carbons, the end carbons, and you now have other carbon written on it, whether it's in bracket or what of view. Are you following, right? That thing is not taken as a substituent, rather a continuation of the what? Of the parent chain. I think there is some kind of structure I'd analyzed in that video lesson I dropped for you guys, something of that kind, complex structures. So if you see that straightforward, if I am to answer, please, it's not an attachment. Expand it. Are you following, right? It's a continuation. I didn't get your question. Why am I? Where I'm streaming it? Because people have refused to understand what happens at GMAETS41. You know, once you join us, I've told you, you must follow us online. There are no two ways about it. Because that is not the channel I'm streaming on. Why do you want to join? You say? You want to go very soon. Just because GMAETS41 has started streaming, you want to go, right? Okay, type GMAETS41 basic channel. A basic class, rather. GMAETS41 basic class. That GMAETS41, don't put any hypersound. Spell it together. Don't put this thing. Just GMAETS41. Then you space basic, you space class. Are you following, right? If you are not on that channel, better do yourself good, though. Going forward, there are a lot of things I'll be releasing. Remember, I've been telling you guys I am test running. I'm test running. In fact, what I am cooking is 99% done. Yeah. Yesterday night, I brought it 99% done. So make sure you follow through so you don't miss out on any important thing. For example, the video lesson on efflorescence, hygroscopy, the liquid sense, do you know it's available on that channel? That basic class. There are some simple things I put there. Are you getting me, right? Then for full-time learning, you come today. This one. Let's move on to the next structure we have here. And this is the structure. The question the examiner asks, JAM 1986. This is our question 3. JAM 86. The question is, which of the structural formula is for pent-2 enoic acid? Which of the structural formula is for pent-2 enoic acid? I love this question. Which of the structural formula is for pent-2-enoic acid? Pent-2, then enoic. Pent-2-enoic acid. Pent-2-enoic acid. Would you? I don't understand you today. Seems like you're not feeling strong. Sorry. Which of the following, or which of the structural formula is for pent-2-enoic acid? This is question 15 under the IUPAC nomenclature something, if you have your past question with you. So in the option, they gave us structural formulas. Are you getting me right? They gave us what? Structural formulas. And they're asking us, which one is the structure of pent-2-enoic acid? You know, we don't have the time for me to be listing, as in writing the options here. Because all the options are structures. All of them are what? So I will go straight and give you the structure of pent-2-enoic acid. And like I said, I love this question because this question also opens our eyes to another area that the examiners can test you on, which is you can be given the IUPAC nomenclature and they're asking you, select out of the options, what is the correct structural formula, like this question now, or what is the correct molecular structure, like this condensation I showed you. Are you following, right? Are you ready? How do you determine or write the structure of pent-2-enoic acid? First thing you have to take note of is the parent name. Is the what? What is the parent name here? Pent. Telling you how many carbons there? Correct. So we are going to write out 5 carbon atoms. So let's go. 1, 2, 3, 4, 5. Good. The second thing is to determine the functional group. To determine what? The functional group. Pronounce this, let me hear. Enoic. You know that the functional group, operating functional group, yes, in the parent name, usually is identified from the ending part of the name. True or false? Like if I say pentane, A, you know it is which homolog? If I say pentene, in, you know it's which homolog? What if I say pentanal, ah, you know it's which alkanal? So here you have pent-2-enoic, oic. Which group is that? Alkanoic acid. Am I communicating? And because this is an alkanoic acid, you must go and indicate the functional group of alkanoic acid. What is the functional group of alkanoic acid? COOH. Which, when we are dealing with all this functional group, I told you it is expanded like this. Is that not so? Good. So I will come over to this, and then on this terminal carbon, I would indicate O and what? OH. Now, there is something I want you to know about the functional group of alkanoic acid. It is always a terminal functional group. It is always what I said. Which means the COOH in alkanoic acid is always carbon number 1. Is always what? Whether you're writing it as a branch chain or you're writing it as a straight what? Chain. You see the COOH, it cannot be within the carbon chain. Are you following, right? It cannot what? Be within the carbon chain. It's not. It can't. If at all this COOH, let me assume it happens to be on this guy now. Let's say I come here and I say OOH. It means that carbon number 1 in this guy will be this carbon. Are you getting me right? No longer anyone here. Do you understand that? That is if the COOH is not here. If I give you a structure and I fix it here, it means that this guy is carbon number what? 1. Therefore, this part will be attachment somehow. Are you getting me right? Please remember, the functional group of alkanoic acid is a terminal functional group. And what does terminal functional group mean? The functional group is always on carbon number what? 1. Are you following? It happens in alkanoic acid. It happens in what I said? It happens in alkanal. It happens in what I said? Good. Which other homologs do we have it on? I think these ones are the key ones. It happens in acid chloride, but you are not exposed to acid chloride nomenclature. It's not, you're not being tested on that. It's not part of your focus. You know, I told you that alkanoic acid has how many derivatives? 4. Is that not so? ester. Ester. It's a derivative of alkanoic acid. I think there also, that guy happens to be a terminal carbon. Acid chloride, the functional group is terminal carbon. Acid anhydride, also terminal carbon. That carbon bearing the functional group is always number 1 by fire, by force. Now, must. That's what I'm trying to let you know. So that whenever you see questions on them, you don't start thinking, which direction is the longest? Where do I start counting from? Go directly to where you see that functional group. Are you getting me? That carbon bearing it will be number what? 1. Let's move on, please. We have indicated the functional group of this guy. Oic. Are you following, right? But take note that this thing is not anoic. Remember, I have alkanoic, alkanoic. This one now is what? Alkenoic. Then you pay attention. When I was teaching you homologs, functional group, did you hear anything enoic from me? No. Something converted to the E. And it's all about you being aware of the prefix. That's why I told you all those homologs, their prefix matters. Are you following, right? Normally, if you come to organic acid, you hear alkanoic acid. Alkanoic acid. You can see this now. Anoic. Are you following, right? This is from alkane. You won't pay attention. I'll give you a knock. You hear the one that say you don't understand. And I'm talking now, you're not discussing. Is that how to learn? When you ask questions, please pay attention. If you don't pay attention, it means you only ask one to disturb the teacher. You ask the question, you pay attention, please. When you ask that question, some other persons are saying alkene, which means some persons understood it already. So my re-explaining, my explanation again is because of you. You're not meant to talk. Let's go on. This thing is anoic. I am taking my time to explain this because it happens in almost every other compound also. In alkana, you can have enal. You can have what? In alkanone, old. Alkanone. You can have enone. In alkanol, you can have what? Enol. It's just at this level, nobody really bothered you so much about, but at least you've seen now, Jump has bothered us with the question. I wasn't the one that brought this. Even if I have a handful of them on our channel, are you following, right? So please pay attention so you understand this. If we meet it anywhere, we wouldn't waste our time. For you to see anoic, it comes from alkane, which means every bond between the parent carbon will be what? Single. Are you following, right? If I now change this into E, it now becomes enoic. It becomes what? What have you done? You have removed the A in alkane to what? E in alkene. Remember, alkene is alk, and then this A will change to what? E. Okay, is that not true? That is just what is happening. So it's 1 plus 1. Which means for us to pronounce this pent2 enoic, there must be an alkene functional group. That's the implication. Are you getting me right? That is a what? Implication. Which means this is not all single bonds. You have an alkene functional group. And what's the functional group of alkene? Double bond. So let's go and find where we are going to fix what? Double bond here between 2 carbon atoms. Am I communicating? Pent what enoic do you have here? Which means the double bond is on the 2nd carbon atom. Counting from where counting should start from. Are you following, right? Or moving from where counting should start from. Now looking at this and the fact we have identified the functional group, where we counting start from here? Will it start from here or from here? From the right. But remember, you still have the choice of transferring this OOH here. I hope you know that, right? Yeah, this is also a terminal carbon. True or false? All right, in this case, counting will start from here. So we go 1. Let's go. This is our interest. Is that not so? Pent 2. So after this 2nd carbon atom, you actually have what? Do you understand this, right? You are done, no? Is there any attachment here? Did they give us any attachment, a substituent? No, so no more stress anymore. But let me assume that we have a substituent here. Assuming this thing is 2-chloro. right? 2 chloro. Yeah. Let's say 2 chloro, 4 methyl. You know, sometimes when we see some of all these simple things, if I take my time to explain it, I'll still tell you, take notes. Something like this could have happened. Structures have been given where there are attachments. Is that not so? So what if this thing was given as 2 chloro, 4 methyl pent 2 enoic acid? Are you following, right? It means after analyzing everything about the parent name, because that is where you start from first. If I give you a IUPAC name, nomenclature, and I said, bring out the structure, your starting point is with the parent name. You don't start with the attachment first. Are you getting me? The attachment is the last thing you consider. So imagine, like I said, if this were to be 2 chloro, 4 methyl, it means we'll come to this second carbon atom and fix what? Chlorine, Cl. And go to the 4th carbon atom and fix what? Methyl, CH3. Are you getting me, right? That's it. Then any other place we need to do any completion, we complete with hydrogen. Are you following, right? So let us complete with hydrogen now. Are you ready? Come over to this. How many hydrogens will this carbon bear? 3. 3. Remember the rule. 1 carbon atom is meant to bear how many hydrogens? Oh no, how many bond lines rather? 4 bond lines. If you look at this, before we start fixing hydrogen, how many bond lines is around this carbon? How many are you seeing now around this carbon? Only 1. I ask you a question based on this one. You are telling me another thing. How many bond lines are you seeing around this carbon? How many bond lines? Only 1. So how many hydrogen will you add to make it 4 altogether? So this becomes 3. If you like, you attach it as CH3. Or if you like, you expand. If you like, you do what? You expand. Are you following, right? If you like, you expand. All right. Then you come over to this. How many hydrogens we go here? How many hydrogens we come here? 1. How many we come here? 1. How many we come here? No. This is pent2 enoic acid. Very simple. Copy it. Let's move on to the next structure. If you have questions, you can ask. I hope this is clear, right? You love it? It's sweet like sugar. Is organic chemistry difficult? Because this is one thing many students fear, they worry about. And I keep saying that, you say, IUPAC nomenclature is 1 + 1, nothing is there. The only challenge that many learners, many scholars have when they are learning it is, you like jumping to the top of a tree without climbing from the what? Base. And that is not possible. Imagine now our building here. From outside, can you jump to the last floor? Can you do that? No, you must start climbing the stairs. Please, the first thing you must learn when dealing with IUPAC nomenclature are the functional groups. The functional groups. Without it, forget it. So when you are done with the functional group, you now know all the homologs. Are you getting me, right? You can now start talking about, okay, let me deal with the namings and other things. Coming to the namings, the principles are very simple. Are you getting me, right? The principles are very, what I said? Simple. Let us look at this structure. JAM 2008. JAM 2008. JAM 2008. I am being tempted to do something. The structural formula was given to us in the question. JAM 2008. In your past question here, it is number 51, actually. Are you following, right? We were given the structural formula like all these ones we used to have. But I want to give you the question using the molecular structure instead. Are you following, right? So we can answer the question there. If you have the past question, you can say that particular structure I'm talking about. So this is question number 3. JAM, I'll be question 4. JAM 2008. JAM 2008. JAM 2008. So you have to give the IUPAC nomenclature of this structure. So I have this. I have this. So you have to give the IUPAC nomenclature of this structure. CH2, CH3. C, CH32. C, Cl. C, Cl. There's a double bond here. And then CH3. So that is the molecular structure of that structural formula given. When I am done, I may have us actually write out the structural formula as given. Are you following, right? So you see that in either ways. This simply tells you that in organic chemistry, your examiner, that's IUPAC nomenclature in organic chemistry, your examiner has 3 dimensions to drag you into. Are you following, right? Can be given the structural formula to state the IUPAC name. Can be given the IUPAC name to give the structural formula. Can be given the IUPAC name to indicate the molecular structure. Are you following, right? I think about 4 dimensions here that the examiner can test you on. Your bag is obstructing me. All right. So we have this. We have to determine where counting will start from. Are you following? We have to determine where counting will start from. What homologue is this? What homologue is this? What homologue is this? Stress the ending part. Let me hear you. Alkene. Alkene. I was hearing alkane. Alkene, because of this double bond here. Is that not so? Yes. Where will counting start from? From the what? The right. What is your reason? The double bond functional group is closest there. Am I communicating? Yes. See, for double bond and every other homologues, from alkene to the other higher homologues, where you start your counting from is where the functional group is closest to. Are you getting me? It is not this thing where you cite your first attachment. That's not the rule we use. It is in alkane we use that rule where you cite your first attachment. Because for alkane, hey, what you have between all the carbon atom is single bond. Are you following, right? So your counting will start from this, right? Therefore we go 1. Do you count this as 2 and 3? No. You know that this Cl represents what? Chlorine. So this is what? 2. Here you have what? 3. This is chlorine attachment. Then you come here. Do I count this one here in bracket as 4? Which one will I count? This one. Is that not so? What is the implication of this CH3 and 2 in parentheses? What does it mean? You have 2 substituents of CH3. Are you following, right? On that carbon atom. Okay. Then you come here. Do you count this one? Okay, you count this one, right? 5. Is that not so? Is that not so? Now let me ask you. Are we ready? Do we count this guy or it's an attachment? Do we count this CH3 or it is a parent carbon? Okay, let me rephrase my question. CH3 here, is it an attachment? Is it a substituent? Because I remember telling you that once any guy is enclosed in bracket, it's substituent. Is that not so? But I still remembered an exception Because I'd said that from our last class, and good enough, somebody asked the question today as well too. Is that not so? Yeah. This is carbon number 5 of the parent. This one, I didn't count it. Is that not so? I'm now asking, is this a substituent, or am I meant to count it? If I am not meant to answer my question, don't explain. Am I meant to count it? Yes. If you are not sure that I am meant to count it, wave me. If you are not sure that I am meant to count it as number 6, wave me. All right. It means you have likely forgotten the rule I gave you. If you have anything that looks like a substituent, an attachment, and it happens that that guy that you are thinking is an attachment is on the terminal carbon. Is on the what? The extreme carbons. Are you following, right? That thing is not an attachment. It is rather a continuation of the what? It is a continuation of the what? Have I not said this severally? Have I not? I have. So please, although this thing is in parentheses like this, it's just to confuse you. It is not a substituent. And I'm still going to prove it to you why it's not a substituent. Are you following, right? I will tell you why it is not a substituent. So this thing is continuation of the chain. Am I communicating? And this is actually carbon number what? 6. Please, watch again. Watch again, because this is an area that students might end up dealing with themselves terribly. Look at the board, all of you. This guy is not number 5. I repeat, this CH3 is not Guinea. It is not. You have to count this CH2 first before you count the CH3. Am I communicating? Am I communicating? You have to count the CH2 first before you count the what? CH3. And this is the reason. If you've observed very well how compounds are being written, organic compounds, you notice that CH3 usually closes. Are you following, right? CH3 usually do what? They close. Are you following, right? The structure. You cannot have CH2 ending a structure except if the functional group there is not single bond. If it is double bond or triple bond, you can answer something like CH2 or whatever. Like in this case now, if this double bond were to be here, assuming this double bond, C on chlorine, I'll be chlorine on this C, and then you now have your double bond. This guy will no longer be CH what? 3. Rather it will become CH what? 2, because one of them has been used in the word bonding. In this case, you are seeing, usually you have CH2, 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 CH2 within. Is that not so? Is that not so? Do you not see that from alkane? Do you not see that from alkane? CH2 are intermediate. They are methylene groups. They are what? They do not form backbones. They do not form end of those, of your structures. They don't. They are always what? Intermediate. Is that clear? Is that clear? So you could not count this guy as number 5 and then CH2 as number what? 6. It's not done. We are done analyzing how this is to be counted. Are you following, right? Yes. In fact, if you have seen the structure in past question, you will find out that this CH3 was placed on top of this CH2. Are you getting me, right? It was placed. Such that if you count up to this as number 5, you now do what? Go up as number 6. It can go down. This can be drawn. That doesn't matter. Are you following, right? And it can even go straight like this. Are you following? Wherever you place it is your choice. So let us give the IUPAC name. Are you ready? Are you ready? Good. So you start with the substituent. What's the name of this substituent? There is a substituent here. And here there is a substituent. Chloro, is that not so? That chloro is on carbon number what? So you now say on the second carbon atom and on the third carbon atom, you have the same attachment, the same substituent, which is chloro. So it's going to be di what? Dichloro. And then you notice as you move on, you have another substituent. Is that not so? Yes. What's the name of that substituent? On which parent carbon atom is it? So on the fourth carbon atom, you have what? Now, how many of the methyls are on the fourth carbon atom? 2 of them on the same parent carbon. So you have to repeat that position of that parent carbon. 4 comma what? 4. Are you following? Then di what? dimethyl. Is there any other substituent? No. The longest carbon chain is what? Is 6. And what is the prefix? So it becomes hex. You indicate the carbon atom upon which we assign the double bond. The carbon atom is assigned to carbon number what? Hex 2 what? So that is that. This is 2,3-dichloro-4,4-dimethyl hex 2-ene. So do you have an option that goes with that? Option C, right? So you see how simple it is. If you want to expand this, you can expand it. The choice is yours. You start with this CH2. If I choose to expand it, if I'm expanding this, this is what it's going to look like. If I'm expanding it to write a structural formula, because this thing in this form is molecular what? Structure. If I'm expanding it, this is going to be, you start with the CH2. Are you following, right? If you like, you distribute the hydrogen. In fact, let me expand everything. Look at it. Hydrogen, hydrogen. You see the carbon bearing 2 hydrogens. And on that same carbon, this one is linked. Are you following, right? I want to fix it here. It doesn't concern anybody. Does it concern you? Does it concern you? In the past question, the CH3 was fixed on top. Are you following, right? And this hydrogen here, does it concern you? This CH3 can take any of these 3 positions as long as it is on that same carbon atom. In the past question, it was placed on top. I could decide, just like Chinedu asked, to bring it down. Are you getting me, right? But I've made my own decision. I fixed it straight. It doesn't concern anybody. Then after that, it links up to this carbon. Is that not so? It links us to what? This carbon number 4, because I've already written out 2. On that carbon number 4, you find out that there are how many substituents? 2 substituents. Remember that this CH3 can still be expanded if you want. Is that not so? In fact, let me expand this one on top. Even if it was written as CH3 condensed. I have decided to expand it. Are you seeing it, right? It's my choice. This is CH3. It's also CH3. Are you following, right? 2 of them are attached to this carbon. After that, you meet this. This is C. The chlorine in that structure in the past question was drawn on top. If I decide to draw it under, does it concern you? Is it still not on that carbon? It's on that carbon. So I'm trying to let you know so you don't stress yourself whenever you see all these things. Get to know that you can play with it. Are you following, right? After this guy, what do you see? Double bond. What next? A carbon. On that carbon, you have a chlorine. If I choose to bring it down, it does not concern anybody. But I want to put it on top. The left theirs on top there. It doesn't concern anybody. After that, the next one you have is what? CH3. So that was actually how the structure was given. So this is the same as this. It's the same as this. Are you following, right? And look at how we refer to that. This structure is called structural formula. It's called what? This guy is called the IUPAC nomenclature or the IUPAC name. And this one is called the molecular structure. If you want to call it molecular formula, no problem. Are you following, right? We are done. Oh. We are done. Let us look at this structure. JAM 1998. JAM 1998. JAM 1998. JAM 1998. Let me check the network situation. We are looking at JAM 98. And this, if care is not taken, might be the last IUPAC nomenclature. Like I said, what we did from our last class, we entered the introduction, defined so many necessary terms. I gave you a functional group of all the necessary homologs. Is that not so? See, that is sufficient with all the information I've given to you to answer the IUPAC nomenclature of every other thing that I have here. They don't disturb you so much in your exams in terms of IUPAC nomenclature. The ones they even give to you are very simple. Are you following, right? It's not those type of things we do in advanced level, 100 level. At the video lesson, I ask people to take. You notice that in each of the video lessons on alkane, alkyne, alkanol, alkanol, alkanoic acid, There were these last structures I always tell you, don't bother. Is that not so? Except on your own you want to take. Those ones, you meet them in your 100 level. WAEC and JAM do not go to that, extent, those type of structure. It doesn't bother you much about it at all. You won't see any such in their previously asked questions. The ones you meet, they are 1 plus 1. That's the truth. What you have seen so far, is IUPAC nomenclature difficult? Is it difficult? Let's look at this last structure, supposedly. Okay, we will take 2 more structures. We'll take 2 more structures. This one, where is it? Just because of the way they scattered this guy. Question number 5. JAM 97. We have CH3, CH, CH3, CH, CH2, CH3, CH2, CH, CH3, CH3. Good. I love this structure. And then the options you have, you've got these options there. Whatever, when I'm done, I'll dictate the options for you. So this is the structure. First of all, if you look at this structure, what would you say that this structure is in terms of the homologue? An alkane, because everything there between the carbon atoms, single bond. There is no foreign body here. Are you getting me right? So this is an alkane. And you know, to determine where counting should begin from, you check the side closest. Where you cite your first attachment. Is that not so? Where you cite your what? First attachment. But of course, while you are doing all these things simultaneously at the same time, you should also be determining the longest carbon chain. Have you determined the longest carbon chain? If I go this way, 1, 2, 3, 4, 5. If you come here, you can either go up or what? Come down. Listen, you can't go up and come down again. Along this straight line, this is the terminal carbon, true or false? So you can go this way to continue the chain. Are you getting me? And in continuing the chain, you cannot go up and come down. It's not done. If you go up, the chain goes that way. The other one becomes a substituent. Are you following, right? Okay, so 1, 2, 3, 4, 5, 6, right? What if I come this way? 1, 2, 3, 4, 5. What if I come this way? Can't I get 6? Let's go. What if I come this way? Let's go. And I am telling you, dear friends, see, but we found out that this guy is also 6. Is that not so? Now, if I ask you this question, assuming you're in the exam hall, you found out that it happens to be like 6 is the longest. Is that not so? In the exam hall, would you prefer to go this way? Or you would prefer to go this way? You want to go this way? The choice is yours. It does not concern anybody. It doesn't concern anybody. Okay, you want to go this way, right? Is that not so? Of course, like I said, go in the direction that will be simpler. Are you following, right? Imagine you bending up and down like this. Does it make any sense? So the longest chain, I want to take this. I'll take this. Are we together? The next thing, since we know the longest chain, we determine where to start counting from. Would we start from the left going this way, or would we start from somewhere the right coming this way? What did you find out? If you start from the left, let's watch now. Let's watch, because something fishy is happening there. Something fishy is happening here. All of you, drop your pen and look at the board. Drop your pen and look at the board. Are you there? Let's go. Is there any substituent here? Yes. Okay, let's go from there. They can either start from this or start from this, or not so? Let's go. You can't come down to get the longest now. You're going this way now, is that not so? But if I go this way now, what do you say about this guy? Substituents. On which carbon atom? Second. So watch. Counting from left, your first attachment was cited on carbon number what? Counting from right, first attachment cited on carbon number what? Do you see the problem now? So, where you cite your first attachment, judging by the first attachment you see, you cannot use these guys to determine. Because both of them is symmetrical. Are you getting me right? Depending on where you count from. If you're counting from the left, you found out that your first attachment appeared on carbon number 2. And on the right, it appeared on carbon number what? 2. So on that basis, can you now say, based on that, you start from left? Can you do that? I start from right. Can you do that? No. No. Now, let me open your eyes to something. This structure we're analyzing now, we have a similar structure also under alkane in that video lesson. I think structure number 3 or so. Now, let me close this guy. Assuming this substituent is not here, because based on the longest chain we are taking, this guy is substituent. Is that not so? Let me say this one is substituent. I decide to go up. This one is also what? Substituent, because it's not among the parent. Now, assuming this guy is not there, let me not catch you right, you know. Let me not catch you right. And if I catch you, you're not looking at the board, I'll send you out. Yes, I'll help you and send you out. I'll help you and send you out. Pay attention. When I say drop your pen and look at the board, I have a reason. Because this thing, you hardly find a textbook that explains it as per why you start your counting from there. The only thing that will help your ministry, if you don't want to use that rule of where you first cite your attachment, if you don't want to use it, you can use the overall rule, which is the side that gives the lowest sum to the attachment. Are you following, right? But I want to use a better rule per se. Yeah, I consider it better. Still going to that direction of where you cite your attachment first. Are you getting me right? So pay attention. But perhaps for this question, I'll show you both of the rules so that you believe in what you're learning. Assuming this substituent is not there. Are you getting me right? When we analyzed this, we found out that our first attachment was seen on carbon number 2, whether from the left or from the what? In that case, you now have your right. You have the right. It is now your decision to choose where to count from. Wherever you count from, you still get the same name. Are you following, right? So if you come from the left, it's your choice. If you come from the right, it's your choice. To still give you 2-methyl pentane. Are you following, right? Is that clear? As if this guy is not there. You decide where to count from. But now let me open your eyes to another thing. The reason why in this case, if this attachment is not there, you decide where to count from is because the attachment you have here is the same attachment here. Are you following, right? They are both methyl. That is why you can decide, okay, it's my choice. I want to start from left or right. You decide it for a structure like this, assuming this guy is not there. Are you following, right? But there is something else that could have happened where you cannot decide. You would have to follow a rule. Assuming the attachment you have on this carbon number 2 and the one you have on this carbon number 2 from here, they are not the same. They are not what? The same. Then that rule of you decide where to come from is no longer your decision. Let me give you an instance. Assuming what we have here is bromine, bromo. It's what I said. Bromine, which is bromo. And here what we have is what? Methyl. You won't decide where to start from. Although both attachments are seen on carbon number 2. Are you getting me right? But what we control where you start your counting from now is alphabetization. Is what? Bromine starts with which alphabet? Methyl starts with, bromine starts with C, B. Methyl starts with what? So since you have bromine here and methyl here, and bromine begins with B, then the rule will adjust. Are you following, right? That you'll be controlled by the first alphabet you will meet when you are reading your ABCD. Are you following, right? So assuming bromine was here and methyl here, where we counting start from? The left. Are you following, right? So take note of that. Now let me remove this. Now let me remove my hand, and then we'll welcome back that other attachment here. Based on these two guys, you say you can start counting from anywhere. However, it's not only these two attachments you have there. We have another attachment. So based on these two, you can't decide where to count from. You move further to the next attachment. Are you getting me right? So let's go again. Starting from here, we have, after this guy, the next attachment you cited is on carbon number what? 3. Let's start from here. That same attachment, this guy, is on carbon number what? Counting from right. 4. Is that not so? So what will now help you to decide where to begin your counting from? This second attachment. Are you getting me right? From the left is on carbon number what? 3. From the right is on carbon number what? 4. Which side is the lowest number? So counting will start from... Are you following, right? That's how you analyze it. But let me use the overall rule, where you will number and determine the side that gives you the lowest what? Sum. If I count from here, 1, 2, 3, 4, 5, and 6. And I count from here, 1, 2, 3, 4, 5, and 6. Now let us look at the attachment position from here. Attention on the board, all of you. You people made this in 100 level. Now you start looking at it as if you have never seen it in your life. Pay attention to this, please. I told you to stop writing. There is nothing you are writing that makes sense compared to what I'm explaining to you now. And if you follow it and you listen to what I'm saying, it will be easy to remember. All this writing is not necessary. If you want to write, go to that video lesson on okay, you will see it there. Are you following, right? But a few, when you just look at, you can easily grasp what we are talking about. Now look at counting from left to right. Tell me the carbon atoms of the parent that bears the attachment. Carbon number what and what? So counting from left to right this way, you have 2 and 3. 2 plus 3 will give you what? Now let us count from the right to the left. Counting from right to left. On which carbon atoms will you see the attachment? Carbon number what? 4 and what? Did I hear 2? I think I have not even finished, Seth. 2, counting from left to right, you have 2, 3, and what? 5. Is that not so? Plus 5. On the second, on the third, and on the fifth, you have this attachment. If you add up this, what will you get? 10. Okay, counting from right to left. Are you there? Your first attachment is where? 2 plus the next one. 4 plus the next one. 5. If you add this, what will you get? 11. Which one of them gives the lowest sum? From the left to right. But what I'm trying to say is I don't like this one. I don't like it. And the reason is simple. I don't have the time to be counting left and right. Before you know, number will fill everywhere. You can do that thing I showed you. Are you getting me right? You notice on number 2, counting from left and right, the same thing. But when you move further, counting from left, you sight another attachment faster. Are you getting me right? Than you see from the right. Okay, I think we are good to go. You can now write. Give me the name of this structure. I have brought you up to the level of confidence. So give me the name of this structure. Remember, this is an attachment. Is that not so? 2 carbon attachment. What will be the name? Ethyl as an alkyl. So, no rushing. You are not competing with anyone here. Go and compete on the D-Day or when you are doing your personal past question review. You can compete with yourself with time. Calmly. I don't want anybody to want to kind of exceed another to say it first. Are you ready? Are you ready? You know where counting is starting from already, so know the number you are giving to me. Let's go. 3 ethyl. I know there is dash. Don't bother yourself. 3 ethyl. Now my question is, why did you mention this guy first? Alphabetization. Are you following? Okay, we go. You people, you are competing. I want to be hearing it one after the other, resonate like choir. Let's go. Now, Chinedu, I was hearing 2 methyl or whatever, I don't know. Look at the 2 here. Are you not seeing that there's another methyl attachment? Are you not seeing it? So you're not meant to 2 methyl. You have to indicate. Since they are the same groups. Are you following, right? Let's go once again. 2, 5, 9, good. Any other substituent? So you conclude with what? Hexane. That is that. That is that. Another structure. So when I am done with this, on your own, if you meet any other structure from your past question, are you following right? You feel you cannot name it, of course, we have our group. Are you following right? where you can just snap and drop and would attend to it. Okay, I have this next question, Q6, question 6. JAM 1998. And this is the structure: CH3, CH2, CH, OH, CH, CH3, and 2. I love this structure. I love this structure. Meanwhile, the options provided for this one: option A, 3-ethyl, 2,5 dimethylhexane. Is that the answer? So no need of reading the other options. The other ones are useless options. I love this structure because this structure, yeah, they gave it a bit like structural formula, but it's not really structural formula per se. It's given in terms of molecular what? Structure. Is that not so? You can see they wrote some things in condensed form and stuff like that. So let us give the name. Now, first, let me tell you something. Based on what I saw in the option, they actually named this thing as an alkanol. As what? An alkanol. And who can tell me why it is possible to name this as an alkanol? OH. Are you following, right? Because OH is the functional group of what? Alkanol. You see, there is a reason why I said this thing. There's a reason why. Pay attention, please. Pay attention. Stop writing as I say this. Stop writing as I say this. Although in the option, they gave the options in terms of alkanol. Are you following, right? As the parent name. But you see, this guy can be named as an alkane as well too. In that case, this OH will be taken as an attachment. Remember I told you that OH is also considered a substituent. It is a choice of the examiner. So in this thing, you'll be getting something like something hydroxyl as an attachment. Are you following, right? And the parent name will now be alkane. Will now be what? Alkane. So it is based on the options given to you that will determine how you analyze it. If the parent names are given in the option as an alkane, then take note that this guy is an attachment, hydroxyl. Are you following, right? But based on the options we have here, which happens in most cases, if you see OH in a single bond structure, are you getting me? Most times the examiner analyzes it as an alkanol. But I'm now telling you it can still be named as an alkane. And there is a reason for that. Alkanol, the functional group, is not a terminal functional group. I repeat, alkanol, the functional group, is not a terminal functional group. Remember I told you for terminal functional group, that carbon bearing that functional group must be number what I said? 1. It doesn't apply to alkanol. For alkanol, the functional group can be on any of the carbon atoms. Are you following? You can't go and say that that carbon atom bearing that OH is number 1. Like in this case, this carbon can never be number 1 in this structure. Are you getting me right? Because the functional group attached there is not a terminal. But hey, look, assuming this thing is COOH, I am assuming, are you following, right? COOH. Then this carbon must be what? Number 1. Are you following, right? Because alkanoic acid is terminal. I've mentioned some structure, at least at this level, for what they're going to test you on. Note, alkanoic acid is a terminal functional group guy. Are you following, right? And alkana is also what? Terminal. Wherever you see COOH, that carbon is always number what? 1 for alkanoic. Then for alkana, remember the functional group of alkanal is what? Functional group of alkanal is what? Alkanal. Alkanal. Functional group of alkanal is what? CHO. I warned you guys about using COH for that guy. COH is alkanal. We have OH. For alkanal, it is what? HO. Are you following, right? CHO. If this guy were to be CHO, this carbon would have been number what? 1. It's by fire, by what? By force. Because this homolog, the functional group is a terminal what? Functional group. But for alkanol, functional group of alkanol is not terminal. That is why this guy can be taken as an attachment. And if you analyze this as a substituent, the parent name can never be alkanol again. Are you getting me right? To end in something. I'll give you an alternative name here. I'll name it as an alkanol, respecting the question and the options provided. And I'll also name it as an alkane, just for your personal knowledge and to beware in case you see that. Let's go as an alkanol. As an alkanol, the functional group is what? As an alkanol, the functional group, the operating functional group here is what? OH. So where you start your counting from to determine the longest chain will be the side closest to what? The OH. Is that okay? You see that the rule of determining where you count from still respects that of alkene. Is that not so? And I told you that's the rule that applies to all other homologs except alkane. It's in alkane you use attachment to determine where to start counting from. The rest, that is how sweet and simple this thing is. The rest, where you start your counting from, the rest homolog is where the functional group is closest. So let us look at this. Let me check from the left-hand side. Going from the left-hand side, let's count. On the third carbon atom, you see your OH. Is that not so? Now let us go to this other side and start. But watch out something. Something fishy is happening here. Are you getting me right? If you go along the straight chain, the last carbon, the last carbon of the parent chain along the straight chain is which carbon? Is it this carbon? You know, going this way. The last carbon along the straight chain is which carbon? Please, my question is based on how this thing is directly now. I'm not asking you of further intricate or further deep understanding you should have. Are you following right? You know already that if you put something in parentheses, by general rule, it is analyzed as attachment, as a substituent. Is that not so? Then you now say except. Forget that except first. Are you getting me right? Forget that except case. Looking at this, along the straight chain, which carbon is the last carbon? Which carbon is the terminal carbon? Is it this one? No. Is it this one? Yes. 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 This is the last carbon, the terminal carbon on the right. And this one, the terminal carbon on the what? Left. Now, if we know that this is the terminal carbon on the right, normally we'll be considering this as a substituent. Is that not so? Yes. Is that not so? Because it is enclosed in what? Parentheses, in brackets. However, are you now seeing the except consideration now? Now you getting me right? We found out that this CH3 enclosed in parentheses happened to be on the terminal carbon along the straight chain. True or false? What did I tell you? Whenever you have something attached to the last carbon along the straight chain, to the terminal carbon, that thing on its own, do you conclude is a substituent or an extension of the chain? An extension, a continuation. Are you following? But another intricate thing here is the fact that it's not just one CH you have there. How many CH3 do you have there? 2. Now listen to this. Listen and listen very well. So that on that D-Day, you may not be wasting your time expanding. You can analyze if you remember this. Whenever this is the case, one out of the 2 is a continuation of the chain. Are you getting me right? What did I say? One out of the CH3 is a continuation of the chain. And one of them is a substituent. One of them is what? On that terminal carbon, on that straight chain. Are you getting me right? Assuming this thing is just CH. Assuming it's just CH3. In bracket, you now know, okay, there's just a single continuation. No substituent at all. Are you following right? But now it became 2. One of the CH3 will continue the chain. And one of the CH3 will be an attachment on this guy. Are you getting me right? This is how the structure actually looks like if you come here. If you come here, if you are to expand it, this is how it looks like. I'll pick this CH3. Having this CH3 and then 2, in parentheses, that tells us that this CH3, 2 of them are on this carbon. Are you getting me right? So I can fix one straight if I want, and then fix the other one down if I want. Are you seeing it now, right? Are you seeing it? Both of them, they are on this carbon bearing the CH. Do you understand this? So that if I start counting from here, supposedly, when I get to this CH here, I'll still continue the chain. Are you getting me right? And this becomes a substituent. Or I will come down, and this becomes what? A substituent. The choice is yours, however you go. Is that clear? Who does not understand this? Question? Please ask.
that like the terminal carbon now is now C2H5.
The terminal carbon, how? This one?
No.
This one? This one?
The one you just gave now.
This one?
Yes. What if it's just one attachment to C2H5?
That is if this guy is not there.
If it's there.
If this thing is CH3 and 2, let him write it. I don't understand what he's saying. Write that there.
What if this is from this now C2H5? Is it possible it can be?
No, you have written H6. I don't understand. It's meant to be H5. Please, you people should remember that rule I gave to you. One carbon must be surrounded by how many bond lines? Are you following, right? So you don't make mistakes. He mentioned C2H5, which was correct. Wrote it and then wrote C2H6. I had to correct it. This cannot be 60. Are you following, right? If you expand it, you find out yourself. The question he asked is it possible for this thing to be C2H what? 5? And then you still have this one again. Is that what you're assuming? If you don't have this. Here in bracket C2H5 like that. And then you still have these 2 here. You don't have the 2. So what you are saying, is it like if I continue this, you now have something like CH, OH like this, and then CH in parentheses C2H5, just like this. Is that what you're saying? Is that what you're saying? I want to be 100% sure before I start responding. Good. When you have this thing simply shows that you have C2H5 linked to this guy. Are you getting me? Are you getting me? Is there any atomicity of 2 here? No. This is purely a continuation of the chain with 2 carbon atoms. With what I said. There is nothing like you have a branch up, you have a branch down on this guy to make one attachment and the other a continuation. It's not like that. This thing, if you extend it, is CH. Let me start from this guy. Are you getting me, right? Come to this. You write out your 2 carbons. Are you seeing it now, right? So it's a continuation of this guy. And then on the 2 carbons, you will see how the 5 hydrogen will come out naturally. 1, 2, 3, 4, and 5. Are you seeing it now, right? That stuff you showed here, what you showed me here is still the same as somebody writing this as CH. From starting from here. Come to this guy, CH2. Are you seeing it now, right? And then CH what? 3. They compressed it. I told you guys something about compression. Do you remember I did something of this kind earlier, right? So if you see something like that, please continue the chain. No attachment there. When you will think of attachment is when the atomicity becomes 2 or 3. Because it can be 3. Assuming this hydrogen is not attached to this carbon. Are you getting me, right? If this hydrogen were not to be attached to this carbon, this CH3 here, how many atoms will it have? 3 atoms. Are you getting me, right? One of them will take the position of the what? Hydrogen. So the question you asked here as to whether this is possible, yes. If it is possible, since it's only one of them, one C2H5, are you following, right? It is a pure continuation of the what? Chain. No substituent there. Is that clear? Is that clear? If there is atomicity, and assuming there is 2 here, assuming, then it means on this carbon, you have C2H5, and you also have what? Another C2H5. They won't be on a straight line. One will take another direction, the other will take another direction. 2 branches. Are you following, right? Then one will be a continuation of the chain. The other will be what? A substituent. So it's still the same thing that is playing out. Are you following, right? Are we good? Now let us count this guy and see. Let us count this and see. Remember we counted from the left. The OH is on which carbon atom? 3. Now let us count this guy from the right. Having expanded it so that you would see it clearly, let us count it from the right. What did I tell you is playing out here? One of the CH3 is what? A continuation. And that will be the last carbon somewhere there. Is that not so? Why one of them is an attachment on this carbon? True or false? Develop your mind's eye now. Develop your mind's eye because I don't want to show it here. Create the expansion yourself. So here we have 1. Is that not so? Which is one of this carbon now, right? One of the carbon is among the parent what? Chain. So here you have 1. Here you have what? 2. Do you understand the counting? Expand this thing with your mind's eye. I've shown you how to expand a moment ago. One of these guys is a continuation, which is the end carbon. Are you getting me? Carbon number 1. Will you count the other one as carbon number 2? No. Rather, you come here and count carbon number what? 2. It is on this carbon number 2 that one of these guys attached to. Are you getting me right? Then you now move to this carbon number what? 3. So do you see we have a problem here? Do we have a problem here or not? We have in terms of where to count from. From the left-hand side, the functional group is on carbon number what? When I counted from the right-hand side, the functional group is on carbon number what? 3. Now, is that not so? Seems like some of you want to punish me to expand this fully. Look at the CH3, CH2, CH, OH, CH. Then on this, you have something like this, CH3. Are you seeing it? And another what? CH3. Look at it. If you like, you bring this one down. The choice is yours. It doesn't concern anybody. So if you are counting from here, 1, 2, and 3. So do you see that respecting the functional group, the functional group is symmetrically placed, true or false? This OH you are seeing is on carbon number 3, whether you're counting from left or what? Right. So based on this OH alone, assuming we don't have any attachment, are you getting me right? Are we following, students? Assuming we don't have any other attachment there, based on this OH alone, the counting can start from where? Correct. God bless your ministry. The counting can start from anywhere and you get the same name. Because this OH is symmetrical. It's placed on the same carbon, whether you're counting from left or what? Right. I hope that one has entered, right? But for this, our structure, we can't count from anywhere. Or do you think we have to count from anywhere? Now let me throw the question at you. Where we counting begin from for this structure? Where we counting start from? Why do you say it should start from the right? We encounter the substituent first, again, closest to the what? Right. Are you following, right? If you use lowest sum, you still get the same thing. Are you getting me right? Yeah, you find out that counting will start from here. If you come from the right, on the second carbon atom, you have a substituent. If you come from the left, there is no substituent there. Are you getting me right? So counting will start from the right. Are we good? Are we good? I don't want to show you guys this. I don't want you to be seeing this. Train your memory, train your brain to be able to understand this without even expanding it. Are you getting me right? Yeah. And like I said, assuming this hydrogen was not there, this could have been what? CH3 and how many atoms? 3. The meaning is 2 attachments exist on this guy. Are you getting me right? And 1 is what? Continuation. Do you understand that? In each of all these cases, one of them will be a continuation. Any extra will become what? Substituent. So counting will start from the right. On which carbon atom did we locate an attachment when we started counting from the right? So 2 guinea, 2 methyl. Any other attachment?
Yes. Because you say that will be considered as alkaline.
Because it is an alkanol, that is why OH cannot be an attachment anymore. Okay, you've remembered what you say. That's my interest. Remember, we are naming this as an alkanol, so you can't take this as a substituent. Are you following? That will be what will determine the parent name. How many carbon atoms do we have as the longest? What is the prefix of 5? Yes. Now, for alkanol, you don't break it at alk. For alkanol, you don't break it where? At alk. Some scholars make that mistake. Just like you break for alkene. You know alkene, you break at alk. Like pen something in, hex something in, boot something in. You break between the alk and the what? In. For alkanol, you don't do that. For alkanol, you break between the and the or. Are you following? So alkan something or. Am I communicating? So for this 5 carbon atom, give me the prefix. Pentan. And then you locate where the functional group is. On which carbon atom? Correct. Very difficult, right? This is simple. It's really meant for people in GSS class. Grade 7 to 9. This type of structure. Our dear friends in the online class, you're welcome to join us. Say you are doing great. Thank you for the appreciation. Martha Mazata. All right, so that is that. And we are actually done with the IUPAC nomenclature per se. With all these things you've learned, if you've been consistent with the class, you attended the last class where we built the foundation, what we have done so far, there is no structure you wouldn't name, at least within the limit of what you are going to be tested on. Are you getting me right? The only thing is that I would have to look for an ester functional group. Ester. Alkano, yes. Oh, sorry. I said I was going to name it according to what? Alkane. And I forgot. Thank you for reminding us. Let us name this as an alkane. Naming it as an alkane, the OH becomes what? A substituent. Is that not so? Then where you start your counting from will be based on where you cite your attachment first. You have the structure expanded in your brain already. You have the mental picture. Is that not so? So as an alkane, if you come from here, we have 1, 2, 3. On the third carbon atom, you have this attachment. And then on the fourth carbon atom, because this will be number 4, is that not so? You have methyl attachment, true or false? If you come from the right, are you there? Here, we have 1 parent carbon, is that not so? 1, and then 2. On the second carbon atom, we have an attachment, true or false? True or false? There's a methyl attachment on this guy. Is that not so? Then you continue. 3. Is there an attachment there? Yes. So once again, we go. From here, if you're counting from right, which carbon atom of the parent will you locate your attachment? Carbon number what? 2 and what? 3. So the first place you locate your attachment is on carbon number what? 3. Sorry, carbon number 2 from the right. But from the left, your first attachment, substituent, is on carbon number what? So where we counting begin from? Are you following, right? Still from the right in that case. But remember, we are naming this as Guinea, as an alkane. Are you ready? I won't name it. We have done the analysis. The longest chain is 5. Is that not so? As an alkane, how would the parent name end? Pentane. Is that not so? So let's go. Begin with the attachment. Or this as an alkanol. Are you getting me? As an alkane, let's go. The attachment here, what is the name? Methyl. I have another attachment. What is the name? Hydroxyl. Oh yeah, let me leave you. I won't say anything because in our last class we've talked about the rule. Let's go again. Have you located the attachment? Yes. Have you determined the name of the attachment? Have you know their name now? Is that not so? Yes. Let's go. You know, the problem with some of you is that you like rushing yourself. And I laugh at you sometimes. You are in a learning stage. And I know. I've been in the teaching field since 2006. No be my case. That time they have not even given birth to most of you here. True or false? Or if they have, you are still in KG class. Not even primary 1. The problem I have with some students is that we like rushing ourselves. There is time to learn. There is time to rush. Are you getting me right? The time to learn, calm down, let everything sink. When you are giving me the name, there are certain basic things you need to remind yourself before giving it to me. But some of you consistently made a mistake. So just calm down, right? You understand it. Don't over-rush yourself. Don't over-put pressure on yourself. So we go again. 3 what? Hydroxyl. We move to methyl. Do you see something here? That the number that came first does not respect the positioning. What it respects is the alphabetization. H comes before M. If I give you dictionary to locate, are you following, right? H comes before M. So it's going to be 2-methyl and no other attachment. So we conclude with what? So this structure and this, they're the same. See, listen, my dear friends. If I give you any of this name, IUPAC name, to write the structure we bring out will be this in any one of them. Any one of them. You get the same structure. So that is it. You love that? You love that? Are you hungry? Are you hungry? Don't worry. We are taking the last question, after which we go on break. This question, I just brought it out. Not really because of anything IUPAC. In fact, it's not an IUPAC question. It's 1993 past question. We were just asked the diagram below, what is it? What is it? Are you following, right? What is that diagram below? So I am going to give it to you so we see. That will be question number 7. I will give the name. I will give the name actually. If need be, let's see. The diagram below are, that's the question. Are you following, right? And then we're given this. Question number 26 in the past question. CH3, C, double bond O, then this, and CH2. I love this question. CH2. And they gave this, then and, there is and there. CH2, no, CH3, CH2, CH2, C double bond O, and then OH. The diagrams below are, that is what was given. And I'll read out the options for you. I'll read out the options so you are ready. Now, option A, isomers. Isomers. Option B, esters. Esters. Option C, carboxylic acids. When you hear carboxylic acid, what comes to your mind? Carboxylic acid. What homologue is that? Oic, alkanoic acid. Are you following? Another name for carboxylic acid is alkanoic acid. I think that carboxylic acid is the common name, the old name. Are you following, right? Alkanoic is the IUPAC. All right, option A, isomers. Remember the question. The diagrams below are, these diagrams, what are they? Option A said isomers. Option B said esters. Option C, carboxylic acids. Option D, polymers. Now, I'm going to use the knowledge of some things that we've known already to ask you to eliminate some things that, some options that are not correct here. I could go directly with the answer, but I don't want to give you the answer directly. I want you to use the knowledge of the known to answer the unknown. Are you getting me right? Yeah. Because the direct answer to this, we've not really mentioned it. Are you following, right? We are still coming to that. And I will say it after we answer this question. Now, the examiner asks you, this thing, these structures you are saying, this compound, what are they? The options I mentioned, one of them is that we have esters. One of the options. I think option B said esters. My question is, these diagrams, are they both esters? And of course, when you are thinking whether they are esters, your mind will go to what? What will help you to know whether they are esters or not? Functional group. Will you play with functional groups? If you play with it, your name is sorry in organic chemistry. There are no two ways about it. I keep saying it. I laugh sometimes when students tend to look at some things. Many students, when we are talking of organic chemistry, their mind goes to structural naming immediately. They never know the functional groups, so they don't know what functional groups of these guys are. But their mind will just go, 5-methyl, 7-bromobutyl. What are you doing? You can't be talking of names when you don't know the functional groups of these guys. You are committing academic suicide. And that is why at the end of everything, the student would still end up having problems with this. But you see them neglecting that function. It's just a crown. Nothing is there. That is where something is there. That is the problem of organic chemistry. Am I communicating, right? So you take note of that. Let's continue. So my question is, these two guys, are they esters? No, they are not. But one of them is an ester. Can you point that one? The first one is an ester. Remember the functional group of ester. What's the functional group of ester? COOR. Where that R is alkyl, chains of carbon, CHD, CH that. Are you following, right? And you see it here. Watch. From this part. From this part. From this part. That is where you have it. Look at COO. This CH2, CH3. This CH3, please. This CH2, CH3 is your R there. Is your what? They are chains of carbon atoms linked. Are you getting me right? This guy comes from, you see this part alone. This part alone comes from alkanol. Comes from what I said? Alkanol. And you see this part? It comes from alkanoic acid. Alkanoic acid. We'll talk about that under esterification reaction, which is acid catalyzed reaction between an acid and a base. Because here we take alkanoic acid as the acid and then the alkanol as an organic what? Base. Just like you learned in inorganic chemistry. Do you remember your neutralization reaction? Reaction between acid and what? Base. But that is inorganic acid and inorganic what? Base. We have a replica of that under organic chemistry. A chemical reaction known as esterification. We'll treat it when we study preparations of alkanols. We are entering preparation of these guys today, you know. Once I'm done with this, you take a little break. We'll chop. I hope you brought food for me, right? I know you never bring. I know. You are always interested. Let's keep him hungry so that he will leave us on time. I will not be hungry. I'll go and buy something from outside. 4:30. Bagam. 4:30 guinea. Bagam. Just pray that it does not enter 5. If you enter 5, it will not become bagam bam. All right, please, let's continue. So these guys are not both esters. So that option that said that the diagrams are esters, is that the correct answer? No, eliminated. If you know the functional group of esters, you know that this guy is not an ester. This guy is which homolog? Alkanoic acid or carboxylic acid. Now, there is another option there, option C. The question said the diagrams are, and option C said carboxylic acid. Do you agree that that's the answer to this question? No. It's only this guy that is carboxylic. This one is an ester. So is option C correct? The only thing now left here is this 50-50 chance of option A and what? D. And these two guys we've not talked about them. Option A said isomers. Option B said polymers. Now, even if we've not done polymers, the word poly, what does it convey? It means large. And when you talk about polymer, generally we use them when we study giant molecules. You know, in organic chemistry, there is a part that is dedicated to polymers. That is where we start talking of carbohydrates, starch. Are you getting me right? They are giant molecules. They are what I said. Now let me show you something about polymers you should be aware of. You can never write a polymer and the structure stops like this. Most polymers, you see somewhere you have N there. You see what? N. I may write a molecule like this, maybe CHO in bracket and then fix N outside. This N means very large number. Are you getting me right? Not as small as 3 atoms, 4 atoms. No, it could be large numbers. Are you following right? Because polymerization as a process is where you have 2 or more monomers combining to form a larger molecule called polymers. So polymers must be very large molecules. Are you getting me right? Very, very large. Your mattress, your foam you lie down on at home is a polymer. At least by God's grace, I've been fortunate to have the experience in the polyurethane industry during my IT. You know, that is at Aguaca there. You know Winco foam industry, right? Winco foam. You will appreciate what you are studying as upcoming scientists. Do you know you can produce a mattress that the size can fill this room? Yeah. This mattress foam we lie down is just some chemicals. We use polyol. There's a chemical called polyol. Then we use methylene and some other methyl chloride components. Gases. This thing, they will feed it into the metering head somewhere. There is a machine called conveyor. From that end there, they would set the temperature, the pressure, everything from the control room. These things from the pipes, from the tanks connected into the metering head on the conveyor. You see some things entering, gases and liquid. They will start reacting. They will enter the conveyor, one horizontal machine like this. You see some things mixing up, and before you know, it's rising. It's rising. It's rising. Like joke. If they don't control it based on the size of the phone they want to what? Produce, the thing will fill the whole room. Big. That is why we have different sizes of what? Mattresses. So that whenever you are saying polymerization, we are not joking. We are saying what is happening in real what? Life. Please, let's continue. So these guys, do you think they are polymers? No, they are not. As a matter of fact, all the homologs we have treated so far, none of them is considered polymeric. Are you following right? They're not. They're smaller molecules. They're not polymers. They're not giant molecules. Therefore, what is the answer? You are correct. And isomers are substances that are formed from isomerization. Isomerization is simply a process of rearranging the molecules of a compound to get another what? Structure. Isomers are structurally different, but molecularly what? The same. And hence, we define isomerization as the existence of a compound with the same molecular structure, but different what? Structural formulas. Let us find out that these guys are actually what? Isomers. Now, look at what we are looking at. We will write the structures. The structures will be different. But if you extract the molecular formula, are you getting me? Which I called molecular structure earlier. The molecular structures will be the same. And how can you determine that their molecular structure can be arranged to be the same? Simply go and calculate their relative molecular mass. Have I taught you RMN?
Yes, sir.
Yes. What is the relative molecular mass of H2SO4? Make we start from there. Because we are going to calculate the relative molecular mass of these two guys to prove that they have the same molecular structure but different structural formula. It's just a structure that differs. You can still arrange them and get the same thing in terms of molecular formula. What is the RMM of tetraoxosulfate 6 acid? You are not supposed to be calculating it again. It's 98. There are some of these things you should have crammed. RMM of CaCO3, calcium trisulcarbonate 4. 100. There are some of these things you've seen again and again. They should be here. Okay, let's move on, please. We want to prove that these guys are isomers. Like I said, for them to be isomers, it means they're only different in structure. They're only different in what? That is their structural formula. Their molecule, the molecular arrangement is the same. Oh yeah, how many carbons do you have here? Count, fast. What's the relative atomic mass of carbon?
12.
So it's going to be 12 times 4. Is that not so? How many oxygen do you have here? 2. RAM of oxygen. It's going to be 16 times what? How many hydrogens do you have here? 3, 5, 8. This is CH3. 8. Is that not so? And RAM of hydrogen is what? Times 8. Oh yeah, solve out this. This is going to give us what? 48, 32, 8. 38 plus 2 will give you what? 40. 40 plus 48 will give you what? Are you sure it's 88? 40 plus. Okay, so 88. This is the relative molecular mass of this compound. The name of this compound is actually ethyl ethanoate. Unfortunately, I have not seen any question on esters. I had wanted to have us give the IUPAC name of one ester. But as we have not seen, no problem. Thank God we've seen this one. Ethyl ethanoate. For esters, if you want to give the IUPAC nomenclature, you start from this part. Not the part that has carbon doubly bonded to oxygen. And are you following, right? You start from the other part that has only one single oxygen. Because this oxygen is singly bonded to this guy. Are you getting me, right? Remember, the functional group of esters is this. Is that not true? So in naming, you name from this part first. And this is how the parent name goes. Alkyl alkanoate. In that video lesson is there. I made, special video on that. Alkyl alkanoate. This part is the alkyl part. And this part is the what? Alkanoate part. I will touch all these things once we enter their preparation and whatever. This part comes from alkanol. From what? During the esterification reaction. This part comes from the alkanoic acid. Comes from the what? Alkanoic acid during the esterification reaction. Are you following, right? So you pronounce this part first before this part. If there are attachments here, you will still pronounce the attachment first. Are you following, right? So look at this now. Where will I pronounce first? This part or this part? The second part, is that not so? Come over here. How many carbons do you have here? 2 carbon as an alkyl. How do you name it? Ethyl. So this is going to be ethyl. Is there any attachment here? No, now. Ethyl. You come here. How many carbon atoms? 2. As an alkanoate, because that part ends with OAte. Are you following, right? Here will be named what? Ethanoate. Let's combine now. The IUPAC name is what? Are you following, right? Now, assuming I have an attachment here, let's assume I remove one hydrogen here. Assume now that I remove one hydrogen. So this is just CH. Are you getting me? And then I have this thing CH2, CH3. Are you seeing it now, right? You know, when you come here, you will start counting the carbon atom from here. Watch. 1. Are you seeing it? 2. Or 1. You know, there's a branch, is that not so? 1. 3 and 2. Which one is longer? So the correct way of moving is this. Are you following, right? So you have 3 carbon in the alkyl part. And there is an attachment. Are you following, right? Did I count this guy among the longest? Did I count this one among the longest? No, now this is 1, 2, 3. 3 direction is longer than 2. Are you following, right? So if you go 1, 2, 3, this becomes what? An attachment. This attachment is on carbon number what?
1.
Then to see where I count from. Did I start counting from 1, 2, 3? You start counting from the carbons bearing the oxygen. Are you getting me, right? So this CH3 as an attachment is on carbon number what? On 1. So it becomes what? 1 methyl. Then this whole part as an alkyl, how do you call it? Propyl. Because 3 is prop. Are you following, right? So let's go. 1 methyl propyl ethanoate. 1 methyl propyl ethanoate. Don't worry, just go and take that lesson. I'll still drop the particular video lesson that contains that ester IUPAC nomenclature. You will love it. It's very simple. You have the whole idea already. That particular video lesson begins with alkanoic acid. But we've taken that one of alkanoic acid on your own. You can still learn more. Learn more, because what we are doing here is just considering having given you the full foundation and taught you just random questions. I'm not taking them homolog by homolog. Are you getting me, right? You can help yourself by taking them homolog by what? Homolog. Learn that of esters. See further structure. I've not seen anyone here so far. I don't have the time for me to start searching. We need to take a break. Okay, let's conclude this. RMM of this, I'm wiping this so we get the original thing we have there. RMM of this ethyl ethanoate is 88. Abby? Has anybody calculated for this one? You've not. Okay, let's go. How many carbons do we have here? 4 carbons. So we are going to still get 48 there. Is that not so? How many oxygens do we have there? 2. Won't we get 32 there? Are you following how this is playing now? But I want to show you one fastest way for you to be able to determine whether 2 or more compounds can form isomers or not. Hydrogen. How many hydrogens do we have? Here, 3. Here, 5. Here, 7, 8. Is it not the same as this? So the RMM of this is, what's the name of this compound? 1, 2, 3, 4. What's the name? What is the name? Butanoic acid. Still 88. We have confirmed. Are you getting me, right? That is how we get to know, yeah, they are RMM, they are the same. Then, although their relative molecular mass are the same 88, this is now the final thing that will help you to know that they can form isomers. Like they are the same thing, written in different what? Form. This is the final thing that will now help you to know. How many carbons do you have here? 4. How many carbons do you have here? 4. They must be the same. You never finish. It hasn't come to an end. There are other different atoms there, apart from carbon. Is that not so? These atoms must be the same in both. How many oxygens do you have here? You have here? Are they not the same? How many hydrogens do you have here? How many do you have here? Are they not the same? Therefore, these guys must form isomers. They can only be written in different structural formats. Are you following, right? If you pull out their molecular structures, they must be what? The same. They must be what? Let me now prove it finally. In overall condensed form, how many carbons do we have here? C4. How many hydrogens do we have here? H8. How many oxygens do we have here? O2. This is how they are written, both of them. In full condensed form. In full what I said? Yes, now look at this CH3. You have your CH3 there. You have this guy COO. Although they're already written in condensed form. If you want to condense further, you come here 1, 2, 3, 4 carbon, you write CH4. There is no attachment. Are you getting me? Nothing is written in parentheses or whatever. So you can condense all those guys. Are you following, right? You can condense all of them, attach the oxygens and the hydrogen. Under calculation of empirical formula and molecular formula in our video lesson, there is one molecular formula I solved that led to ethanoic acid. But when we got the formula, it was for ethanoic acid, I think C2H4 and then O2. It gave us something like this. And I named it in that video lesson. You can reach out for it. Video lesson on empirical formula and what? Molecular formula. So that is it. Please, this is how you get to know whether things can form isomers or what? Not. Rule number 1, which is most important. Those 2 or 3 different structures given to you, the number of different atoms you have in them must be what? The same. Exactly. The must, before you talk about the form isomers. Then if you calculate the RMM, it must be what? Equal. Now, on the basis of this, let me give you the final thing. Are you ready? CH3, CH2, 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 CH3. Look at this. Oh. Are you seeing it? I have CH3, CH2, CH, CH3, CH2, CH3. Are you seeing this? Are you seeing this? Can I wipe this guy? I want to show you another one. CH3, CH, oh no, CCH3, CH3, CH3. Are you seeing this one? Are you seeing this one? Yes. Now look at these 3 guys. The structures. Are the structures the same? Are their structures the same? Are their structures the same? What you are saying, the way these structures are like, is it the same thing as this one? Is it the same as this one? No. 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 But if I tell you all of them are pentane-related compound, will you argue it? All of them are pentane-related compound. Pentane, how many carbons do we have there? How many carbons do we have here? Count it. How many carbons do we have here? Count it. How many carbons do we have here? Count it. So in terms of carbon atom, they have equal number of carbon atoms. True or false? What again do you need to use to determine whether these guys can form isomer, whether they are isomers or not? Hydrogens, is that not so? How many hydrogens do you have here? 12. How many do you have here? If you have not counted, count it. If you never count on now to find out that it's 12. Have you counted? Is it 12 or not? Some persons have not counted. And some persons don't even know what they are counting. Now let's count it together. How many hydrogens do we have here? 5, 6, 9, 12. Come here. How many carbons do you have here? 5 carbons. How many hydrogens? You can count 3, 3, 3, 3. 3 times 4 will give you what? These guys are isomers of pentane. You know, part of the exam question they ask you is how many structural isomers can so-so compound have? I've just shown you one. Pentane has how many possible isomers? 3. Pentane can be written in 3 different forms. This is normal pentane. Normal pentane. You can use N-pentane for it. Normal pentane, N-pentane. Normal. These guys are called isomeric pentane. Sometimes you see them as I-pentane. I-Guinea, which is isopentane. Isoguinea, pentane. So this and this, they are isomers. Isomers of pentane. Isomers of 5-carbon structure. Are you getting me right? Their structural formulas are different. But if I write their molecular formula to be the same, let's see it. How many carbons altogether here? 5. How many hydrogens altogether there? 4. Write for this one to be the same. Write for this one to be the same. That is the overall condensed state. Are you following, right? One more before the break. See, I'm using this one to also teach isomer once and for all. I've defined it. I've defined isomerization. The existence of a compound having different structural formulas, but the same molecular what? Formula. Oh no, sorry about that. I think I mentioned the year so you can trace. Where is the year even? Think JAM 1993. Question 46. And the past question is question 26 there. Okay, look at this guy. There is this compound called alkoxy-alkanes. You don't study them. They are not part of your focus in terms of studying. The functional group is something like this. Alkoxy-alkane. You have oxygen singly bonded to alkyl groups on its left and right. Are you following, right? So look at this. Then look at this guy. Tell me the homologue that this compound belongs to. This compound I want to write now. CH2OH. You don't know of this. You don't know it. I've told you. This is an alkoxy-alkane. Alkoxy-alkane. This thing is always written in such a way that you have an alkyl on the left, alkyl on the right, oxygen between them, and the oxygen is singly bonded. Are you following, right? CH3 is what? What's the name? CH3. Methyl. So a met group. Are you following, right? Alkoxy-alkane will not be methoxy-methane. Methoxy-methane. Alkoxy-alkane. Are you seeing how this is going, right? That's why you must know the homologue name first. Are you following, right? But like I said, don't punish yourself of alkoxy-alkane. You don't study it. Even in 100 level, you don't study it. The only reason we bring in alkoxy-alkane is because it is isomeric to one homologue. And I want us to get to see it as we take our break so that I can chop and come back for the next 5 hours. Which homologue is this? Alkanol, is that not so? Yes. Question. This guy and this guy, are they isomeric or not? Are they isomers or not? I gave you the key formula that helps you to determine whether some things can form isomers or not. So these two guys, are they isomers or not? Why do you say they are isomers? The number of carbons, how many in both? Oxygen, how many in both? Did you verify the hydrogen? Oxygen, you said there are 6? No, 1. 1 in both. Did you verify how many hydrogens? Yes. How many hydrogens? 6. That's correct. In both, is that not so? So alkoxy-alkanes can be written as isomers of what? Alkanols. This guy is ethanol. Ethanol is isomeric to what? To methoxy-methane. Ethanol is isomeric to methoxy-methane. And let me show you what happened. It's just rearrangement, like I showed you how I moved all these carbon atoms and rearranged. Are you getting me? Look at what happened here. Watch. Watch very well so that you not miss out. Watch very well. I want to show you what happened. Such that what happened to this alkoxy-alkane in rearrangement of the carbon structures and whatever atom you have there to get this guy. Are you ready? Look at what happened. We moved oxygen from here to this place. For oxygen to come here, we needed to remove one hydrogen from here, so minus 1H. Minus Guinea, I said. So that this CH becomes CH what? 2. The oxygen you moved from here picked the one hydrogen you extracted from these 3 hydrogens. Are you getting me, right? So if you pick that one oxygen plus one hydrogen, you get OH. You get what? Look at it. And this CH3 reduces to what you said? CH2. And look at, I can still write this isomer. Is there another way? Okay. I think ethanol does not have any other way you write it. Because if you move this guy to this place, if you move this guy to this place, then these 3 will reduce. Are you getting me? One hydrogen will come here to still give you CH3, CH2OH. So these are the isomers there. And I have helped you to open your eyes to how you can determine whether some things are isomeric or not. See, to get your isomers is just for you to carefully remove one atom from here. As you are removing it, something is coming there. But if I remove one atom from here, I'm taking it to somewhere. This somewhere, I will remove something from there. Are you getting me? Watch what happened here. Watch what played out here. CH3, CH2, 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 CH3. Oh yeah, let's go. CH3 here. Are you seeing it? I didn't change anything. Is that not so? CH2 here. Did I change anything? Come in here, you notice something happened. Is that not so? How many hydrogens here? How many hydrogens here? So I remove one hydrogen from here. Is that not so? Now watch. When I remove that one hydrogen from there, Notice that I brought CH3. Is that not so? Look at it. I brought this guy here. Are you seeing it now, right? Remove one hydrogen from here, took it to where I brought the CH3 from. Are you following, right? Are you following, right? If you remove one hydrogen from here, this becomes C, what? Good. Then the CH3 comes and takes the position of the hydrogen leaving. Look at it here. Then the hydrogen that left will take the position of this CH3. The CH3 is linked to this carbon. True or false? True or false? So the hydrogen going there is actually linking to this carbon. If that hydrogen attaches to this hydrogen, how many hydrogens altogether? Are you seeing it now, right? How did I get this one? Still similar. Let's go. You notice you have that you have your CH3 here. Look at it. Is that not so? CH3, CH3. Then I came to the second carbon. Let's assume this. And we'll find out that that second carbon is not bearing any hydrogen. Is there any hydrogen on it? Is there any hydrogen on it? Which means you have to do something to this hydrogen. True or false? True or false? But the best thing to do is simple. The best thing I did to get this one, I actually maintain this CH3. Remove this CH2. Are you getting me right? I removed that what? CH2. I removed it. So pull it out with your mind's eye. Have you removed it? Have you removed it? So that this CH3 will be linking to this directly. Are you getting me right? Then watch. As I remove this thing from here, this carbon here, is it bearing any hydrogen? So I'll remove this hydrogen. Are you following right? Removing this hydrogen because this CH2, I'm bringing it on top of this. Are you following right? This hydrogen will now link up to the CH2. Are you getting me right? If the hydrogen links up to this CH2, this guy becomes CH what? So we come and take the position of this hydrogen. If I were to expand this, you know that this hydrogen could have been written here. True or false? True or false? Now. So this CH3 moves. H here will link up. You get CH3. Are you following right? So this CH2 will come here, link up with this. You get CH3 on it. So that here you have CH3 linked to this guy. CH3 linked. CH3 linked. CH3 linked. You get this structure. So isomerization is just rearrangement. Are you following right? And when you rearrange, you get different structures that are molecularly the same. It's not our break time. Coming back, we'll be looking at preparations and properties of these homologues, starting with alkane first. All right, friends in the online class, you are welcome to join. We are done. The remaining part we are going to take won't be streamed. Preparations and properties, but I'll make a little revisions on that via our channel, so you can actually always stay tuned.